This is a hypothesis test for a population proportion, single sample. A polling agency claims that over 40% of adults shop for a gift within a week of an event. In a random sample of 2,730 people in the United States, 1,130 said they shop for a gift within a week of an event. Test the agency's claim at the alpha equal 0.10 level of significance. So we need to set up the null and the alternative in terms of the population parameter. This is a test about a proportion, not a mean, so the parameter I'm going to use is p, not mu. So the claim is that over 40% shop for a gift within a week. So as a mathematical statement, that's going to be p greater than 0.40. The case of equality is not implied here. So this is going to be an upper tail test. This is the agency's claim. This makes this the alternative. The null statement contains the case of equality. P is equal to 0.40. So the pieces that are given in this problem are the sample size and p hat, the sample proportion. So we need to know, can we use the one proportion z-test for this problem? To check that, we need to find the product is n times p at least 5 and n times 1 minus p at least 5. These two would give us, if these two conditions are met, then we have the justification to use the z-distribution for our standardized test statistic and for the critical value or values. So our sample size is 2730. P is the value from the hypotheses, and we want to know, is that going to be at least 5? Well, 40% of 2,730 is going to be at least 5. Specifically, that's 1,092. So this condition is met, and we have to check the other one. And 1 minus p is the complement. So if p is 0.40, then 1 minus p is going to be 0.60. So in other words, is 60% of 2,730 at least 5? Well, it's definitely going to be more than 5, but we can get that product very easily. Okay, so both of these are at least 5. So we can go ahead and use the normal approximation to the binomial, which means that our standardized test statistic will be a z-score, and our critical value will come from the standard normal table or our normal CDF function in the calculator. Our standardized test statistic follows the same structure as the test statistic for a test about a population mean. However, it is not the same formula. It's p hat, our sample proportion, minus the claimed proportion over the square root of p times 1 minus p over n. Now, we don't use p hat in the denominator because we assume that the case of equality from the null is true. So we're assuming that that proportion is 0.4 until proven otherwise. But the structure is the same. It's what we observed from our sample minus what is hypothesized, and then we need to divide by some sort of standard error specific to the sampling distribution. So in terms of a structure, it's very similar to the hypothesis test for a population mean when sigma is known, but we are using different pieces. Okay, so inputting into the formula, whoops, I made a mistake up here. This is not p hat, sample proportion. P hat is equal to x over n, where this is x. My apologies. Okay, so p hat is going to be 1,130 over the sample size. So we need to write that sample success in terms of a sample proportion. Again, I apologize for that. So I can get this rounded or converted to a decimal. I can carry it out 3 decimal places approximately. Okay, so our sample proportion p hat minus the hypothesized proportion over the square root of 0.4 minus 0.6 over that sample size. Now it is a little cumbersome to get in the calculator, and there is a way to get the standardized test statistic directly from the calculator. But if you want to put this formula into the calculator, I strongly suggest using parentheses for the numerator expression, and that denominator expression is all under the radical. So I get a standardized test statistic of about 1.493. So what we observe from the sample proportion, is 1.493 standard deviations away from the middle of that standard normal distribution. Now, we're probably going to end up failing to reject the null, but to know for sure, we're going to need to find the critical value. The critical value is, there's only going to be one, and it's going to be positive because this is an upper tail test. And we need our level of significance, which indicates the amount of area I want in that upper tail. It's also the probability of a type 1 error. So drawing the standard normal curve, shading this upper area of rejection and indicating I want 0.10 amount of area in there. I can either use the standard normal table and read in the body of the table to 0.90 and then outward to find the z-score, or I can use the inverse normal function in the calculator. Going to my distribution menu, selecting inverse normal. Now, because my tail is shaded to be left, I can put in that cumulative area to the left of that upper critical value and leave it as is, and I will get that critical value of 1.282. Or going back to that distribution menu, if you have a newer TI-84, you can put that tail area in directly and indicate that it's a right tail. Either way, see, you'll get the same critical value. Now, looking at the critical value, comparing it to the standardized test statistic, I was incorrect. I thought, given this was less than 2 standard deviations away from the middle, I thought we would be failing to reject the null. But hypothesis test results can be surprising. My standardized test statistic is in the rejection region. So at alpha equal 0.10, my decision is to reject the null. Now, because the claim is the alternative, the correct way to say this is that there is sufficient evidence to support the agency's claim that over 40% of adults shop for a gift within a week of an event. Now let's go ahead and find the corresponding p-value. The p-value is going to be the area further out in the tail, going from our standardized test statistic to positive infinity. So in probability notation, that's the probability we get a z-score greater than 1.493. You could certainly use your normal CDF function in your calculator, but I'm going to go ahead and show you how to get the standardized test statistic and p-value all in one spot. To do that, you want to go to your stat menu, arrow over to tests, and you want to select one proportion z-test. One meaning we're working with one sample, proportion, and the conditions are met to use the z-distribution. There is no other option, so if the conditions aren't meant to use the z-distribution for this test, you would have to either not state that you're unable to do the problem if you're an intro to stats class and you're not covering other methods, or you would have to use another method. Alright, so you want to put in the value from the hypotheses, the claimed value, that's 0.4. X represents the number of successes, and that was 1,130. Our sample size was 2730. And then you can change the direction of alternative. That's important. You need to have the correct direction, because you will, if you don't, you will not get the correct p-value. Okay, so looking at the standardized test statistic, it is a little bit different than what I got when I did this quote-unquote by hand, but there is some rounding involved when you do the formula by hand. So I strongly suggest, if you are in my class, to use technology whenever you're testing a claim about a proportion or finding a confidence interval about a population proportion. Just because rounding issues greatly affect your answer, and you definitely want to be close enough to get the problem correct. Okay, but in terms of making the decision though, our decision wouldn't change. Okay, rounding to 3 decimal places, this is 1.485. When I got this by hand, I got 1.493. Looking at where this is placed with respect to the critical value, the decision is the same. We are going to reject the null hypothesis. Oh, and looking again at the screen, underneath that test statistic is the corresponding p-value. So that p-value is 0.069. That's the area further out in the tail from our standardized test statistic, and we're comparing it to our level of significance. 0.069 is definitely less than 0.1, so the decision would be to reject. If I changed my level of significance, however, to 0.05, the decision would change. The p-value is no longer less than the level of significance, it's greater than or equal to. So if our level of significance was 0.05, the decision would be to fail to reject the null. So it is possible to reject at one level of significance and fail to reject at another.